Okay, thanks once again for inviting me to the seminar. And my name is Błażej. I currently work at Lyft. I'm a staff research scientist there. But like the work that I will be talking today about was from before, when I was still working with Deep Sense, University of Warsaw, and actually partially also during an internship at Google Brain. So there's actually quite a few of institutions, as you can see, who contributed to the model-based reinforcement learning for Atari. Okay, so let's get started. So I will start with this first part of presentation, and feel free to ask any questions during the presentation. Also, I mean, might be a bit easier if you actually switch on the camera so that I actually see that like you react or not react, but if possible. And then at the end, I would also like to share a little bit more about what I'm currently working on the autonomous driving. Okay, so let's get started. Okay, so that's the paper. As you can see, not only many institutions, but many authors. It was a spotlight at iClear 2020. I mean, there's like, we have code on archive. There is the open code is open source as a part of tensor to tensor library, which I'm not really sure, but I'm not sure how actively it's still developed, but I guess you still should be able to run it if you can downgrade your TensorFlow. And it got like 180 pluses on Air machine learning, so I guess it also counts for something. Okay, so like thanks to Vadim and your perfect introduction. So you are well aware about what's model-based methods. So I will briefly give it kind of like a context in what we are doing in this work. So maybe one word of a motivation. So the main reason why we wanted to do this work is to see how little data you actually need to learn a reasonable agent for playing Atari, right? Because I mean, like the Model 3 agents are pretty good, but I mean, they will not take less than like a few millions of frames to interact, right? Which is kind of like hours of playing the game. And if you think about this, like human can play the game, like learn to play this game much faster, right? I mean, probably they will not be expert on this game, but I mean, it will be enough to play for 5 minutes to at least get the idea of like how to play this game. So our idea, like we wanted to see, okay, like can we actually push these agents to push these algorithms to use very little data from the real environment and really see some reasonable performance. For Atari game, I mean, you might argue that's maybe not that super important because Atari is a lightweight simulator, and I mean, computation is cheap, and that's probably true. But like, if you start thinking about other applications, like for example, dear to my heart, autonomous vehicles, then like collecting any real world data is quite expensive. Especially, it's like super expensive. You actually need to deploy your own policy to collect this data. Right, because maybe you are not sure if this policy is so good, and like if you want to put it on the car, I mean this is causing like a potential safety risk. So this is very dangerous. So like if you can develop methods that use fewer, like smaller amount of data to train, this would be super important. So how our training loop works? So first it starts with collecting trajectories with the current agent. At the moment, like at the beginning, it's just kind of random agent. Then, like similar to David's word model, like we train a word model that is something that can predict what will happen in the future based on the data. Next, we use this word model and train an agent inside of this. And for this, we use a standard Model 3 algorithm, like PPO in our case. And then we take this new policy and we deploy it again to the real world, or like in this case to Atari simulator, to collect a little bit more data. And this data is then used to improve our word model. So actually, like if you compare it to the initial work of word model in David and Schmidhuber, this is actually, they are doing just one loop of this thing. So they collect random trajectories, they train a word model, train an agent, and they have an agent. But we actually have discovered that like it's important to actually do a few loops of this training if you want to deal with more sophisticated environments, even even for Atari, you will need this already. Does it make sense? Okay, so yeah, let's talk a little bit about the world model. So in our case, how the world model works is it takes like last 4 frames of the environment. It takes the action and predicts next observation and reward. And I guess the difference between this and, again, another difference between this and David's world model is that we are predicting the full observation and not just encoded state. Yeah. By the way, we are actually working on this more or less in parallel. So I think we had the first version of our work at more or less the same time as, maybe slightly later than David's but we are just working on a little bit different environments and have a different approach to this. Okay, and what's important is that once you have an world model that can generate a next frame, we can actually use it as a simulator, right? So we take 4 frames from the game, we predict a next frame, but then we can move this next frame to the input and use this taking next action to predict yet another frame, right? And so on and so forth. So basically, if you have a world model which is predicting just 1 frame into the future, you can actually employ it to have a simulator that can unroll for arbitrarily long. Well, I mean, whether it is arbitrarily long or not, it depends really on the quality of simulator, because of the quality of the world model. Because if it starts making bad mistakes, then the whole unroll will diverge from anything that you would observe in the real environment. So here are some of the examples how well the simulator can work. Right. So on the left you can see predicted, and in the middle you can see ground truth. So you will see that this, for the game of Breakout, I mean, this is almost pixel perfect, right? What we can predict, which is pretty cool. And for the game on the right, which is Crazy Climber, I mean, it's not exactly perfect, but it's also predicting a reasonable play, right? So I mean, it predicted the opponent, the eagle or something, dropping this X. It predicted a different moment, but it's still kind of a reasonable gameplay. And maybe something that I have forgot to mention is that the overall amount of data that our models were trained with is 100,000 interactions with the environment, which is, which is much more, around probably 20 times less data that a PPO would need to train to master these games. Okay, so so one would say that, Atari seems to be pretty simple, so it's not that hard to create a world model for this. So I mean, it takes us quite a bit of time and people and effort to actually make it, and kind of some things that you would probably not think immediately what's complicated. So, for example, the model has to learn to count up to 21, right? Because that's kind of a score that's there. Also, the ball is very small. So if you are comparing these frames with kind of some naive, L2 loss or something like this, I mean, it will be pretty easy for the model to forget about the ball and try to predict the other parts of the environment. Also, the actions control one of the paddle, for example, the paddle on the left, but the right paddle is actually controlled by somehow the built-in AI, right? So maybe the AI is a bit too much of the word, but in the original Atari game simulator, there was some logic to control the right paddle, depending on what's happening on the screen. So the model also have to learn to mimic that AI. And it's also kind of that when there's a point scored, the ball will disappear for some moment. So the model has also learned to bring it back. Oh, sorry. So apparently one of the videos got broken. Sorry for this. Okay, so there will be no video, but I will tell more or less what is important here. So as I mentioned before, if you don't, it's easy to forget about small elements, right? As the ball in the case of Pong, even though it's crucial for the gameplay. So the way to fix it is that you want to clip your L2 error or clip your cross entropy error if you are using that one. So that is that like you don't really punish the model for making small mistakes of the color of the background, right? So it's kind of like a slightly different brown color. You don't want to punish that one. But like you do want to punish the bigger changes between like bright brown and white, between the color of the ball and the color of the background. So this way you will actually, like if you start clipping this error around 0, you will force the model to, instead of optimizing the exact color of the background, you will rather like force it to focus on the smaller items maybe, but which are like striker difference in the color. And also another thing which helps is that we make the model also predict a reward, not just outcome or not just observation. And like for the reward, like being able to predict where the ball is also crucial. What is more, so Atari games are...
do I understand correctly that this is a per pixel loss, that you're subtracting the pixel from a pixel, and then if you have, as far as I understand, in the per pixel loss, if you have the ball, if it's 1 pixel wrong, it would be the same loss function as if it would be in the other side of the screen, right? The per pixel loss would be the same.
Correct.
So this seems to be the main issue, and I wonder if have you thought about applying some different loss function that would take into account whether the ball is close or it's far?
I mean, I guess that like you can think about this to actually predict, maybe introduce different loss, but kind of like what we wanted to avoid is, designing a loss per game, right? So kind of like Atari is kind of like a suite of like 50 games, like we are evaluating ourselves on like 20 something games, and kind of, like you don't want to have a hand-coded term saying, oh, there is a ball which, you need to track the location of the ball, right? So like you want to keep very far from this. Definitely, like you might consider about some, additional loss maybe of like continuity of the scene somehow, but yeah, like we didn't explore it.
I wonder if something like optimal transport would work there. So in optimal transport, you measure the difference between two distributions, not per pixel, but by how far you have to move one to get the other. I'm not sure if it's easy to implement as a differentiable loss. That might be impossible to implement as a differentiable loss. I'm not sure, but sounds like a good metric.
Yeah, potentially this would be a good idea. So I guess what saves us here as well is also that usually the elements are slightly more than 1 pixel, right? So there's actually like a few pixels, right? So then they will have kind of like an intersection in consecutive frames. So maybe this helps a little bit. But in fact, like with a very tiny elements, that the model do struggle, and we'll see this in a moment. So maybe that's a good extension. Another thing is that Atari games, the simulator itself is like deterministic. There's kind of like no built-in stochasticity, but that's not true if you are looking only at the last few frames to predict what's the future, right? And in this game of the Kung Fu Master, I think that's the name of the game, you can see what's happening, right? So the ground truth is predicting, for example, like 2 opponents coming, but the model is predicting a few more, like 4 or a different type of opponent. So here you can see that the model is predicting like reasonable futures, but not always exactly the same what would happen in the real world. Okay, so let's talk a little bit about what model did we use, because I think that's the kind of like the most probably sophisticated part of the work. So like we started with like relatively simple autoencoder, right? That would, or almost autoencoder, that would like take 4 frames, will go down to a bottleneck, add their action, and using this per pixel log its loss, it would then produce the predicted frame and the reward. So that was like what we started with, and I mean, it worked like kind of well for some of the games, but with many games it struggled a lot. It was just like too weak of a model. So one of the problems the model had was that it was ignoring actions. And it's actually not that easy to notice this problem, because like, so suppose that you had some expert trajectories that you train the model with, right? I mean, it's not, and then you evaluate how well the model works again with the same expert. I mean, if the model is ignoring actions, you will not notice it, because the expert is giving you again the same actions that they had in the real game. So we actually had to do like an interactive visualization in which at each moment you can actually decide what will be the action taken by the agent. And then you will see, oh, I'm asking the Pong paddle to go up, but it's actually going down. So this means that the model learned to ignore the actions. So the way to combat this was we just kind of like make sure that the action embedding is very strong. So we actually have it like the input action is encoded first and then multiply and added at the every layer of the up convolutional part of the model. So it's kind of like has like a lot of signal for the input action to make sure it's there. And then are the other like improvements to the model? So this is the whole huge upper part of the model. And how does it work? So during the training, it kind of cheats, because like during the training, it takes also not only the input frames, so like not only the previous frames, but also the next frame actually. And based on the next frame and multi-head attention, it's built a discretized version of the next frame, and it puts it in this discrete latent. And then this discrete latent is then passed over to the bottleneck and used to predict the future frame. So I mean, you can see that in a cheating in a sense, because like we have the next frame on the input and we also have the next frame on the output, right? So it's kind of like it's trying to push as much information as it can through the discrete latent. In order to make the life a bit harder for the model, we introduce noise on after the discrete latent. So it kind of the model has to learn to predict the future frame even when the discrete latent is noisy. And then the other important thing is that we train this bit predictor, which task is to, based on the also input frames, is to predict how a discrete latent will look like, but without looking at the next frame. So then this bit predictor is what we will be using during the evaluation. So during the evaluation of the model, we cannot cheat anymore. Like we cannot like use this whole tower with attention and pixel embedding, the upper part. So instead, what we can do is use this bit predictor, which was previously trained to predict a reasonable discrete latent, taking into account this input frames. The reason why we use, so like this is like similar to video models as, for example, SV2P, but those are using usually not discrete latent, but continuous latent. And I mean, the reason why we decided to go with discrete, I mean, so there are two things. So like one, for a continuous, due to the way how you train them, such variational autoencoders, you need to have a parameter And for us, it would mean training a separate, like optimizing a separate parameter for each game, which was not good. And then the other thing is also that the game are kind of like discrete nature, right? So I mean, these are like Atari games, which have maybe some discrete objects and so on. So we kind of had this intuition that discrete latents will work better. And we had some experiments with this, and in fact, this is what worked the best. Does this make sense so far?
Yeah, I think so. Yeah, and thank you very much for really talking about the process of how you got into this solution, because it's really valuable.
Sure. Okay. So here we'll show off some of the examples of the pixel perfect games, and maybe not so perfect in the moment. So like, on the left, there's a game of Freeway. I think that's actually a very interesting game, because this is about a chicken crossing a road and avoiding these cars. And yeah, and you can see that like our model is practically not, I mean, it's making almost no mistakes. And similarly for the Pong, I mean, this is doing a pretty good job. So let's look for like this benign error. So the one on the right we have seen previously. So this is where the model is predicting a possible future for the game, but slightly different than the one that would really happen in the reality. On the left, you can see like playing bowling, right? And then the model predicts that the ball can actually go like, split into two. So I mean, this is clearly an artifact, but luckily this happens only after the scores were computed, right? So I mean, so it's not really affecting us. And this is an example which goes very close to what Vadim you mentioned about this one pixel things. So on the right-hand side, there's a kind of like space game, like defending, I think, against aliens, Earth, or something like this. And actually, what this game is missing are exactly the bullets. So I mean, but to be honest, even if you take a look at the video at the resolution that like YouTube can support is, I mean, you will not see the bullets neither in the ground truth nor in prediction, because I think that they are literally single pixel. And yeah, and this is somewhere where the model will struggle. Maybe if we can like increase the capacity of the model somehow, or maybe add some more loss. And like similar here, the like 3D game in which we drive a tank, and I mean, it predicts pretty well, but yeah, it struggles to predict correctly the bullets, right, or like the missiles, so which are actually pretty important part of the game, as you can imagine. And finally, there's a few games where there are some games where we totally failed. I mean, so this one is, I think, called James Bond, and then I think that the problem with this game is that it changes kind of a lot, because like if the James Bond gets out of the frame, then the whole game changes a lot, and I think that this is very tricky for the model to learn. So I mean, like, so it still kind of fails on some of the games, but yeah, it caught something about the game, right? Like, I mean, like we can see that there is something jumping, but yeah, not very well. Okay, so we went through the first part, which is how the model word model works. So what about the agent training? So this word model we can now use as an imperfect simulator of the environment. And what is kind of like important for our goal to use as little real environment data is that we, when we collect the data from the model, like we don't really use the environment anymore, right? So kind of it would be like so we are not accessing here the real Atari simulator, we are only using simulated environment. Kind of like a technical detail, but it was actually like take us a lot of time to implement, was that like we implemented PPO inside TensorFlow graph. I mean, this was still yet TensorFlow 1.0, which was not that user friendly. But like thanks to this, we had also kind of like both the word model and the algorithm was both executed in TensorFlow graph on GPU. So like we didn't pay the price of like copying data between GPU and CPU. And in general, I mean, it worked faster than otherwise would, even though it still was pretty slow. Another important idea, and or maybe like a slight trick that we use to work for this, is that we kind of noticed that the unroll of the simulator works well for limited number of steps, right? So probably like 100 steps into the future, you could still predict a reasonable outcome. But Atari games are pretty long. So I mean, like you can sometimes need like as much as 1,000 steps to play Atari well. And I mean, and this 1,000 steps, I mean, like you don't, like we didn't really expect that the model will be able not to diverge from the reality. So what we have done instead is that we started doing this random start. So like we had a few trajectories from real world, and in order to train the agent, we didn't train it for the whole trajectory always, but like we selected random subsections of this trajectory, and we fed them to train the agent. So the agent would start at the beginning of such a subsection, and then unroll in the world model maybe for like 50 or 100 steps. And this was kind of like giving us the flexibility of being able to train in the world model, but not like without paying the price that the world model is diverging from the reality a lot. So yeah, so this shows that it's pretty good. Okay, so so this is how we decided to show the scores. So if you take a look at the one of this graph, I mean, on the left-hand side, we compare against Rainbow. On the right-hand side, about like PPO. And what we compare is how much more data would Rainbow or like PPO need in order to match our performance of algorithm, right? So the red line here is 100,000 frame or 100,000 interactions with the environment. So this is kind of what we use for the training, right? So kind of like if you would like to train, for example, Freeway. Freeway is one of our favorite games for this reason. If you would like to Rainbow to match our results on Freeway, it would need to train for like 1,000,000 frames, right? So it's 10 times more. For on the Kung Fu Master, it would require like 4 times more interactions with the environment, right? So we kind of like see that there is kind of like a significant improvement on most of the games. I mean, not all of them. So for example, like Bank Heist is one of the games that like our world model really had serious trouble modeling. And here, I mean, like the model-free approach is actually better. We also kind of maybe one thing, and this is also a difference compared to this work models work from David Ha and Jorgen Schmidt-Huber, is that we and I mentioned to you this before, that like we have made like 15 loops or like many loops of like collecting trajectory, improving world model, training agent, and doing this once again. And the reason for this is that kind of initial random agents, and this goes to also to the example that Vadim showed, right? Is that like if you are exploring with a random agent, maybe you are not exploring very interesting part of the environment. So maybe you didn't really explore the cliff or the place where the treasure is, right? So for this reason, you actually we have seen the same thing. So like you need to have a little bit of random data, which gives you initialization of the world model. But then the agent that learns to play in this world model will not be able to, go outside of what was explored by the random agent. So once you train in this initial world model and agent, it will be smarter about exploration than the random agent. So if we deploy it once again to the real environment and to the real simulator in this case, it will collect some more interesting data, which will help to improve world model. Yeah, and we have measured that, up until the 15 epoch, the 15 loop, I mean, we are still improving. So this iterative nature of this process is important. It was also some results on kind of tuning some additional hyperparameters such as gamma, which maybe not that important. Yeah, so maybe one more question is like whether we should be using, so I think which was kind of different from this work compared to other works on world models, and this kind of like also Dreamer v2 version is that like we're predicting in pixel, not in the latent space. So, like we are predicting the whole observation actually, right? And I mean, then this is kind of like might be debatable whether that was a good idea. Maybe, instead of predicting pixels, we should just predict like a latent space. And that's true, it might be easier, but exactly the last point will be more difficult, because like if you predict some latent space and then you collect new data, you will have to change the latent space, right? So like after each iteration, you will basically have to start from scratch with the latent space and so on. So I mean, so there are some works who deal with this, but I have not seen a work which is trying to do this with this low data regime, right? I mean, so we're just using like 100,000 interactions from the environment. I have not seen those. I mean, like there are some works which do it pretty nicely, but I mean, they would like use 10 of millions interactions, something like this. Okay, so maybe let's complete this with some funny example of what an agent can learn. So this is a game of a kangaroo. So like how a human would play this game is like control this kangaroo from the bottom left corner to go up to the upper right corner to find the small kangaroo that's a mommy kangaroo that's looking for a small kangaroo. But like actually we'll see that our agent is not doing this, it's just kind of standing in place, but still it's collecting some points. And to understand why it's collecting points, you will have to look very closer into this, is that there are sometimes like missiles, or this is actually, I think, a coconut or something like this, falling on the kangaroo. And what the agent has learned is that instead of going up through the ladders and so on, it can actually kind of like hit the coconut, which gives you additional points. So that's kind of like an example of like, where RL does something a little bit different than what we would expect, because I mean, it has found a different way to optimize the amount of points. Yeah, and also kind of like sometimes the world model tends to be makes funny mistakes. So for example, be very adversary, making the paddle as long as the whole game, or creating additional boxer in the boxing game, making this not as fair as you would hope. Yeah, so that's all what I had about the presentation on model-based Atari, and I would be happy to answer questions if there are any.
Yeah, thank you very much for this talk. I'm still thinking about loss functions for screens. I think you can, for example, blur the images and measure the loss function on the blurred images, and that might help.
Yeah, I guess this would be a risk that like with the blurred image, you can actually lose some of the smaller parts. I mean, I'm pretty sure that you would, I mean, like even in the kangaroo example, I'm pretty sure you will like lose this small coconut that is kind of like falling, right? I mean, it's, I'm not even sure like if you can see this through the virtual, through the screen sharing. So, I mean, it's kind of, it's very small. So, yeah, it's, for example, now falling in the middle for this. So, okay, so.
It's hard to see on.
Yeah. So if it's hard to see like this, I mean, would you be able to detect this when you blur the image?
Yeah, but if you measure the loss between, so you measure the difference between between generated image blurred and real image blurred. So the images are generated unblurred, but the loss function compares two blurred images. So
I see.
And then if it generates it correctly, then the loss is 0, just as it should be. But then if you miss by 1 pixel, the results is still good, because the blurred images will be similar.
I see. So I guess it depends on the blurring algorithm, right? But kind of like if it blurs like together like 5 by 5 pixels, something like this, right? Then if there's just kind of like 1 pixel different, I mean, it might decide the algorithm that it's actually easier, to forget about this 1 pixel which is different.
Oh yeah, that might be the case.
Okay, there's some question on the
people are offering their solutions, like use guns.
About smaller part. I mean, using a gun is something that, I mean, I think we consider, and I think we run some experiments. I mean, I don't think it improved here the situation, but I mean, maybe this was not optimized a lot, because that's true that the discriminator in principle could catch this, these things as like a missing ball, right? So this is not huge for like a L2 or a cross entropy error, but it should be easily detectable by the discriminator. I mean, so like again, like we've done some experiments with this, which I don't think were very well, but I don't think we pushed it that hard. I mean, this could probably help.
We definitely have several directions for the next paper here, so maybe it will become new research. Yeah. Well, thank you for this talk. Does anyone else? I don't think I have any more questions. Does anyone else?
True. Yes. So there's a question about how to transfer this approach to a real-world task like a self-driving car. It seems too hard to build a world model for visual observation. Yes, I agree. It is hard. I mean, like potentially, I mean, you could, use it not on kind of like a visual observation, but on some kind of like mid representation, right? So I mean, actually, like often what you do actually we'll be talking this in a moment, but what you sometimes do is kind of instead of learning the car to drive, from a raw input of the camera, you first parse the scene around, right, and generate, for example, a top-down view of like how the situation around the car looks like, right? So kind of like a top-down map with lanes and with your ego car and different cars around, right? So maybe on such a representation, maybe a world model would be already feasible. But I will actually mention about this in a moment, that kind of like what we've done for like this kind of data-driven simulation is actually predicting like agent's location and not the whole images, and this works pretty well. But it involves kind of like more, hand engineering, because we know that there are cars around, and these Atari games, we didn't want to parse the images. We kind of assumed that, that there's unknown number of objects and that we don't really track it, and we do it unsupervised, right? So if you add more human knowledge, you can do it better.
An important strength of your work is that it's pretty universal, right? It worked on so many games without any fine-tuning.
Yes, correct. I mean, so
yeah, parsing the map might hurt it, because you'd have to parse for a particular game.
Correct. So like we literally optimize our solution for maybe 2 or 3 games, and then we deploy on a suite of like 25, and like most of them worked.